Hi, this is Mr. Mac, and this is a video talking about linear relations and functions. Now, in the last video, we talked about the difference between a relation and a function. And let me say that most linear relations are functions, but we do have vertical lines that are linear and they are not functions. So a lot of times we'll say linear relations and functions. Now, first of all, a linear function is one whose graph is a straight line. Now, if you look at the word linear, you can remember this because it are a line. Anyway, if you have an equation, y equals mx plus b is the way we define a relation to be linear. Now, what you have to see is that the exponent on the y is 1 and the exponent on the x is 1. So anytime you have an equation where the exponent on the x and y are both 1 and the x and y are not multiplied together, those would be examples of linear functions. Y equals 2x plus 3, y equals 1/2 x plus 4 divided by 7, 5x plus 7y equals the square root of 19. All of these things are linear. Examples of things that are not linear would be anything that has an exponent other than 1 on one of the variables. If you had 27 equals x squared plus y plus 3, this would not be linear because of the exponent of 2. If you had 19 is equal to x times y, this wouldn't be linear because this term right here does not have a degree of 1. We'll talk about that later, but if you have x and y multiplied together, it's not going to be linear. And then if you have anything like 14x plus 17y plus 19 times the square root of x equals 2, this would not be linear because when you have a variable underneath a radical of any type, that is not first degree. We'll talk about that later too, but this would make it not linear. And maybe one final thing, if you have y is equal to 1 over x plus 2, when the variable isn't in the denominator, it's also not linear. So these would be examples of functions or relations that are not linear. Now, and you will need to be able to look at equations that generate ordered pairs, in other words, having both x and y, and tell whether their graphs are linear or not. Now, the next thing that we want to talk about is a thing called standard form. If you have a linear relationship, let's say you have y is equal to 7x plus 3/2. One of the things that we would like to be able to do is to change this equation, which is actually in slope-intercept form, into a thing called standard form. Now, standard form is when the equation is in the form ax plus by equals c, where all three capital letters A, B, and C are integers, and they are to have no common factors. In other words, if they all have a factor of 2, you would divide that out. And we want A to be greater than or equal to 0. In other words, if a is negative, then you should multiply through by -1 to get a to be positive. And that would make the equation be in standard form. Now, as an example, let's just go ahead and take this linear equation that I have drawn for you here, or written for you here, and let's put it in standard form. Notice first, we want the x term plus the y term, and then on the other side of the equal sign, we want the constant. So if you look at this, the 7x really needs to move over to the other side. We can do that by subtracting 7x from both sides of this equation, minus 7x minus 7x. Now I'm going to write this as negative 7x plus y equals 3/2 over here. Now, at this particular point, 3/2 is not an integer. We need an integer there. One of the truths of mathematics is if you take any fraction and multiply it by a multiple of its denominator, your answer will not be a fraction. So the easiest thing to do here would be to multiply 3/2 by 2 or some multiple of 2. Now we also know that we don't want the negative sign in front of the 7. So we can get everything done at once if we multiply both sides of this equation by 2. So, excuse me, -2. So we'll do that. -2 times negative 7x is 14x. -2 times y is -2y. And -2 times 3/2 becomes -3. And now we have standard form for this equation. Now the next thing we are talking about here is the intercepts. Now an x-intercept is where the graph will cross the x-axis. In other words, it intersects with the x-axis. And a y-intercept is where the graph will cross the y-axis. Now, let's take a look, for example, at just a simple little x-y axis here. And let's put some points on the x-axis. And let's let this be -3, -1, 2, 4, 7. This point right here, this point, actually has coordinates -3, 0. This point has coordinate -1, 0. This point has coordinates 2, 0. This point has coordinates 4, 0. And this point has coordinates 7, 0. Now, if you look at this diagram or picture, you'll see two things. Oh, and this point has coordinates 0, 0. Every point on the x-axis, and these are all points on the x-axis, have coordinates where the y-coordinate is 0. Now, that should make sense to you because the coordinates actually tell you how to get from the origin to where you are. And so if we consider for just a moment this point, the point 4, 0, the coordinates tell us go 4 units to the right of the origin, and then don't go up or down at all. And that would keep you on the x-axis. And every point that's on the x-axis, we haven't gone up or down, so y would be 0 in all of those cases. Now, we can use that in finding x-intercepts, because if we have an equation to find the x-intercept, set y equal to 0. In other words, put 0 in for y and solve the equation for x. Now, if you think about it, that would mean that any points along the y-axis, we would have gone up or down, but not left or right. Let's call this 0, 2, and this 0, 5 maybe, and this 0, -1. Notice also that any point on the y-axis has a 0 in the x spot. And of course, notice that the origin has a 0 in both the x and y spot because it's on both the x and y axis. But what we can do here is to find a y-intercept. What we'll do is we'll set x equal to 0 and then solve for y. So to find the x-intercepts, you'd put y equals 0 in the equation and solve for x. to find the y-intercepts, you would put 0 in for x and solve the equation for y. And we're done.